Hey, and welcome to another episode of the Critical Science Podcast. This is Dr. Lyle Burgoon. Today I wanted to talk to you a little bit about some tips for assessing science. So I was on the plane just the other day coming back from a court case. And, a person next to me found out I was a scientist. They didn't find out. Told them I'm a scientist, and so we were talking about, how is it that, the general public should go through and should assess, when they're seeing a scary story in the press about science. And that got me thinking, well, how many tips do I really have? And, in that conversation, we talked a little bit, and then I sat down, I started writing them out. And so I got 7. I made it to 7. All right, so I've got these 7 tips, and if you're watching on YouTube, you can see them on the screen. But if you're not, if you're listening to the podcast, go to the site, critscipod.com. That's critscipod.com. Go there, and I'll have them there for you that you can look at. It's this big image. You can go through them, and see them a little bit later on. So the first tip I have, and this is actually kind of important. It doesn't matter who paid for the study. Judge the science on its own merits. And what I mean by this is there's a lot of cases where, and this has happened to me before. So I was working a case and the reporter said, well, aren't you just a shill for this company? Why should we believe anything you have to say? And that's not cool. What I was doing was I was trying to explain the actual science. It doesn't matter who paid for the science. Industry could pay for the science. Government could pay for the science. At the end of the day, somebody has to pay for it. Because at the end of the day, this is somebody's livelihood. We are scientists. That is our profession. Somebody has to pay us so that we can then pay our bills, right? I need to put food on the table for my kids. I got to pay for my mortgage. I got to pay for everything, right? I got all these different expenses I got to pay. Somebody has to pay me for this. So it doesn't really matter who pays for the science, right? Industry, let's say the pesticide industry does a study and they're going to submit this to EPA. Does EPA say, oh my gosh, the pesticide industry paid for this study? Oh, we can't trust them. No, that's not what they do. What they do is they actually look at the study and they say, okay, so yeah, you had enough animals in this study. You guys used concentrations that are human relevant concentrations. It looks like you guys didn't forge anything. All your numbers seem to make sense. So yeah, this looks like decent science. And that's really what, as scientists, we try to do, is we try to assess the science, based on its own merits, rather than, now there are other scientists, and I've run into this at meetings all the time where people say, oh my God, I can't trust you because you've gotten money from, I don't know, CropLife Europe. Yes, I got money from CropLife Europe, but let me tell you something. This work that we did is solid, good work. Now, if somebody finds something wrong with it, let me know, right? But let the science stand on its own merits, because at the end of the day, all of us get paid. Academics get paid, especially in toxicology. Academics in toxicology have to find something wrong with what they're studying, with the chemical they're studying. Otherwise, they won't get more research money, right? So now I'm not saying, because it was an academic study paid for by the National Institute for Environmental Sciences, that study's bad. No. What I do is I go and I look at the study and I say, oh, hey, look at this. You guys found a really cool result. It just happens that this is at a concentration that is 50, maybe 100 times higher than human relevant concentrations. Now, as a toxicologist, I can figure that out. But the lay press, may or may not report that part of the study, right? And it's certainly not going to go into the press release. We had a situation just the other day. I'm on the Children Health Protection Advisory Committee for the EPA. We had a situation where somebody was presenting some results, and they didn't actually follow through and go through all the different papers to eventually see that, this effect that I'm reporting on is actually not at human relevant concentrations. That was something I picked up and I called them out on. Now, so scientists aren't always doing a very good job of this either, but we all need to do better. Like I said, who paid for it doesn't matter. What matters is, what is the science actually saying? My second tip is everyone should be a lot more skeptical, especially reporters. Reporters are supposed to be trained to be skeptical. Not seeing that much right now. I'm not seeing a whole lot. I'm just seeing people regurgitate mostly what is within the press releases from the universities, and that's really not cool. To me, that's not actual journalism. That's just regurgitating, some kind of PR thing that goes out. So we need to be skeptical. We need to be skeptical about these studies that we see that are being reported in the press. We need to be skeptical and look at the claim. And we need to ask ourselves, okay, so if this is an epidemiological study, how many people are we actually talking about? Not the top line numbers, but when they start actually talking about the actual effects, how many people is it that actually showed this effect? And was the study randomized? If the study's not randomized, then it's probably not very useful. Most epi studies are great for generating hypotheses, but they're horrible for policy. And I know there's going to be a lot of public health people out there who are going to be really angry with what I just said. I don't care, because it's the truth. Epidemiological studies are observational studies. And what you probably learned back in maybe 4th, 5th, or 6th grade science is we start with an observation. Based on that observation, we create a hypothesis. Then we test the hypothesis. And through that testing of the hypothesis, we start getting to causal type of information. So did this chemical actually cause this or not? We can only really get that when we do actual randomizations. Now, I'm not expecting that you're going to be able to read the study and say, oh, this was randomized or not randomized necessarily. Sometimes it's hard. Usually, though, a good study will say right up front, we randomized and this is how we randomized. If they don't tell you that they randomized, they probably didn't actually randomize, which means you should be really, really, really skeptical. Studies that have a small number of people in them are also probably not very, very informative. Studies with fewer than 1,000 people, not going to be very informative, which is why when you look at your clinical trials, especially phase 3 clinical trials, unless it's for a rare disease, we're talking thousands of people are used in that trial. And the phase 2 trial before, there are probably hundreds to thousands of people used in that leg of the trial as well. So what I'm saying is, for us to really have good evidence in humans that something is happening, we need to have thousands of people. All right. Now, the other thing, the other flip side to this is, you got to think about the population, which is the next one, number 3. The population. It actually matters. Who were they looking at when they did these studies? Where do these people come from? A lot of studies, especially in the social sciences, are typically college students. I was one of those college students who, would participate in various psychological studies at my college in order to, get extra credit in like Psych 101 or maybe in social psych or something, right? The population matters. So if you're looking at a study that only looked at healthy males who are college aged, and you happen to be someone who is in your 40s or 50s, and, you don't have a lot of those same characteristics as those college kids, do you? So those studies probably are not going to be very useful in making inferences from that study to your situation. An example I've seen recently at the US EPA, the EPA is trying to use a children's health study to set worker safety standards. Let that sink in. For formaldehyde, EPA is using a children's health study. And not a particularly good one. It's a pretty bad study. And it's an epidemiological study. And they're using that to inform a safe level for workers. Now, it's been a while since I've actually read the law, but I'm pretty sure that in most states, children are not allowed to work in hazardous conditions where you would typically find formaldehyde in the workplace. Children typically are not allowed to work in those kinds of conditions. You typically have to be 18, actually, to work in those kinds of conditions, because at that point we feel that you're an adult. So a study of children where the children are like, low teens, tweens, first graders, second graders, that kind of thing, that really doesn't inform me about worker risk because it's the wrong population. We should be using a study in workers to inform about worker risk. I mean, just common sense things like that, right? The population matters. Don't use a study on people in China to influence any policy about people in the U.S. We live very, very differently. For instance, the air quality in Beijing is horrible, and we don't have many cities in the United States that have that level of bad air quality, right? We also have genetic differences between populations in China and the United States, right? So there's whole kinds of reasons why we can't just draw inferences from these studies in Chinese people, the studies in children. Same thing for Europe. Europe is not nearly, the same as the US. There are lots of differences economically, everything else. So it's hard to use studies in people in Europe to make inferences about the US. Same thing for Africa, right? It's just, we have to be studying the population that we're interested in. And that's a common sense thing from statistics. Number 4 is also from statistics. We need to accept uncertainty. Uncertainty is real. It's pernicious. You avoid it at your own peril. That's what I typically tell my clients. Here's the problem with uncertainty. Just because a scientific study says that a particular dose of a chemical is toxic doesn't mean that it is actually toxic. That's one study. There's all kinds of uncertainty around this. And so it's hard for us to really get a grasp on this uncertainty until we really study a problem really, really, really well. But one study doesn't make something that I can draw a judgment on. I need multiple studies that are reproducing that first one, that are reproducing it really well to see if this is a real effect. One of the things I like to tell people, going back to statistics, most of the ways that we analyze biological data, toxicological data, et cetera, pharmacological data too, right now is what we call frequentist statistics. And frequentist statistics is not that much different. Actually, it's not different at all from how statistics at a casino works. Now, you might drive by, at least where I grew up, there would be billboards for casinos, and they would say that they had a certain payout rate, right? And so the thing you got to remember is that payout rate that the casino is talking about is as you run the game out to infinity, to an infinite time, right? We will have this kind of a payout. And that's kind of the same thing that happens with the statistics in these studies, is they're only valid if you do an infinite number of that study. And that's what it's based on. But we're not doing an infinite number of that study. So what happens is a better way to think of it is this. You have a coin. Now, let's do a better one. You have a dice, a 6-sided die, okay? You could do this with a D20, if you're a D&D fan, but we're just going to do 6-sided because it makes the math easier for my head. So you got a 6-sided die, and you're trying to figure out, is this die weighted or not? Actually, I was watching Inception on the plane, and that was one of the little tokens that they used there. Anyway, so you got the 6-sided die, and you want to figure out if it's weighted. Will one throw tell you if it's weighted? No. Will 2 throws tell you if it's weighted? No. You're actually going to have to do a lot of throws in order to figure out whether or not it's weighted. Same thing with a coin. You flip a coin, right? And I'm assuming that there's no trickery with respect to how you're flipping and all that stuff, and I mean, there's all these physics things. Anyway, the bottom line is, if you were to flip it a few times, you're not going to be able to figure it out if it's a fair coin or not, just off of one throw. You can't do it off of 2 throws. In fact, when you run the simulations, it's typically going to take somewhere in the neighborhood of 50 throws. Now, when you're talking about a 6-sided die, it's going to take more than 50. It's going to be close to 100. I forget what the number is. I ran the calculations a long time ago. Needless to say, it's going to be hundreds of throws before you get this accurate, right? And so now, think about that. So if it takes that many coin tosses, 50 coin tosses, before we can actually say whether or not this coin is fair, right? You with me? It takes about 50 coin tosses to figure out if a coin is fair. It is completely unreasonable to expect that one scientific study of a chemical is going to be able to tell you anything about its toxicity. That is just absolutely crazy talk. But here's the problem. We use one study all of the time. NIH, National Institutes of Health, they do not want to pay for reproduction studies. The U.S. Environmental Protection Agency does not want to pay for reproduction studies. Nobody wants to pay for a study that reproduces another study. Nobody wants to pay for it. But here's the problem. For something as simple as a coin, it's going to take me 50 tosses to figure out if it's fair, to figure out what, that heads comes up 50% and tails comes up 50%. It's going to take me close to 50 throws. It could be more than that too, right? It all depends. But on average, it's going to be about 50 throws. So now we're going to take something that's as biologically complicated as an animal or an in vitro system, which is cells and a plate, and we're going to try to say, oh yeah, this chemical is safe just off of this one study. The only way to do that is you have to have a lot of animals or a lot of replicates of the cells. That's the only way this works. Yet, we don't do that. We don't reproduce the studies. We might have one study with an N of 20. Well, guess what? We need to reproduce that study several more times, right, before we can accept it. Because remember, a coin, 50-50, I need almost 50 throws. How many replications of this am I going to need in order to, before I really feel comfortable about, how well I know something? So we need to accept that uncertainty. We need to accept that it's real, but at the same time, we need to accept that I can't accept one single study, because with one single study, I have no idea what the uncertainty is. I have no idea what the mean is. I have no idea what the effect size is. The effect size is basically what the chemical or the drug causes in the animal versus the control, right? So like sometimes we'll dissolve stuff in water, sometimes we'll dissolve in corn oil, soy oil, different things, right? But at the end of the day, here's the thing that's most important. We can't just do this off of one study alone. And there's this uncertainty. And the only way to get at that uncertainty is to do the study multiple times. Here's one of my favorite ones. Good scientists are humble. Good scientists acknowledge the strengths and the weaknesses and the unknowns about their work. That's important. If you're reading a study and you don't see an acknowledgement of the strengths and the weaknesses or the unknowns, that's a problem. That's a red flag. That tells you, I got to be careful with this study. Scientists make mistakes. We know we make mistakes. And we need to be, as scientists, welcoming of other scientists pointing out our mistakes and helping us identify when we've done wrong and how we could do better. The other thing is, good scientists, they don't do this science by press conference crap. There's a lot of this. And this happened with the women's health study, way back when. I forget when it was, the 90s? It may have been the 90s. When the advice came out that women should avoid hormone replacement therapy. It was a horrible study. Poorly done, lots of things wrong with it. There's a whole book that you could read. I'm going to try to find that while I continue to talk to you about this. But here's the bottom line. When you have scientists doing science by press conference, what you're really having is you're having scientists say, hey, look at me, we're doing all these great things. Oh, the book, here we go. The book, oh, come on, is The Menopause Manifesto. It's by Jen Gunter. It's a really good book, but she has a passage in there where she talks about science by press conference with respect to hormone replacement therapy. We shouldn't be having scientists do press conferences like that to announce their work. Right? That yes, we should be proud of our work. Yes, we should be trying to get our work out there. That's not how to do it. Okay? Because we need other scientists to ruminate on this and to figure out, is what you did right or is it not right? Is there something wrong with this? We should avoid going out to the public with our stuff immediately and saying, hey, look at us. I have no problems, like if I'm on LinkedIn, the general public is not generally on LinkedIn for me, right? I will share, hey, I just published this paper. If I just a couple of weeks ago, hey, we just published this paper. To me, it was a very important, probably the most important paper I've published so far in my scientific career. I'm going to push that out on LinkedIn. That's totally cool, right? Am I going to push it on Facebook? No. That's not where all my scientist colleagues are. I do not friend most scientists on Facebook. The ones I have on Facebook are ones that I know very well personally, who are I actually consider to be my closest friends, right? LinkedIn's a different thing, right? So yeah, good scientists are going to put their stuff out on LinkedIn because that's how we help other scientists find it. But, don't go to the press. Don't go to the public. Oh my gosh. All right. Number 6, check your biases. This is good advice for critical thinking in general. We all have biases based on our experiences and training. But to be critical thinkers, we need to recognize our biases and control them. It's the same thing reporters are supposed to do too. We need to recognize that we have biases. We need to recognize what these biases are, and we need to hold them in check to ensure that we go out and we find all the information that we need to find. Basically, what I'm saying is if you like a particular thing, maybe you're conservative and you're ingesting Fox News, that's great. I'm happy for you. But if you're going to go make a important decision, don't just make your decision based on what you're hearing from conservative media, consume other kinds of media to help you see other sides or where the blind spots are. And with science, it's the same thing. Don't go looking for, if you know that you believe that all chemicals are toxic, which all chemicals are toxic at the right concentration, don't forget that caveat. But if you believe that all chemicals are toxic at all concentrations, then you probably should burst that bubble and go look for other information that doesn't necessarily confirm your biases. That's what number 6 is about. Number 7 builds off of number 6. Avoid confirmation bias. This is important for critical thinking and for good science. Good science and critical thinking are based on the idea that you're going to look for evidence that proves your hypothesis is wrong. Not that your hypothesis is right, but that it's wrong. Only looking for things that confirm your biases is actually pseudoscience. And unfortunately, most of what I'm reading today in the toxicological literature is pseudoscience for one reason or another. So those are the tips. There's 7 of them. I hope it's not too many for you. I think they're all pretty good. And like I said, you can get these tips. You can get these from critscipod.com, the Critical Science podcast website. You could probably, I think I'm going to also post them at the Toxic Truth blog as well in a couple of weeks, probably not right away. I have a few other things that need to go up first. But definitely critscipod.com. And I'll just scroll back up to the top. There you go. So 7 tips for assessing science. There you go. I think most people could really benefit from these. So, definitely share this with your friends, your family, anyone who can read, pre-readers. Hey, kids who are learning to read, I don't have too many big words. I got a couple, right? Like stereotyping, that's a pretty big word. So maybe not quite pre-readers, but early readers. Yeah. I think this would be really good for them. There's not too many words. There's lots of pretty colors. I think they'll really like it. Anyway, with that, thanks for listening to the podcast. I'm Dr. Lyle Burgoon. Have a great day.